find errors fast and focus on what matters. By the end, you will filter error lines, quantify log levels, pick the latest incident, rank urgent events, and run quick keyword and searches over logs. You will see how a tiny Python pipeline turns noisy text into actionable leads during an incident. I'm Professor Pi, teaching search and incident investigation from basics to practical Python. Logs are noisy. They mix routine info, warnings, and real failures. Success means you find the signal quickly. In an investigation, you want a short list of candidate lines to read now. Simple text filters and small indexes often win over heavy models when you need speed and explainability. The trade-off is semantic depth. Text filters miss some paraphrases that a semantic model might catch, but they are fast and transparent. At a high level, we are converting raw lines into structured clues. Think of one line as a record with a timestamp and a level and a message. We will filter by keyword, count levels to measure noise, pick the most recent error for triage, sort by severity plus recency to prioritize, and build a tiny inverted index to answer two-term queries. This pipeline shines on windows of hundreds or thousands of lines and gives sub-second feedback in a lightweight script. We will build a small readable toolkit that outputs the error lines to inspect. A level frequency table, the most recent error, the top urgent events, and a keyword intersection search. This snippet creates a tiny raw log stream and filters it for the word error. This snippet builds a compact string with 4 example log lines and splits that string into a list called logs. A simple list comprehension scans each line and keeps only those that contain the token error. The result is stored in errors and preserves the exact original lines so you can read the full context. Printing errors shows the concrete error entries you would start with during an incident. This gives you the immediate set of lines to examine first. Next, we turn lines into a quick counts table to measure how noisy the window is. This example pulls the level token from each line and turns those tokens into a frequency table. The list levels is built by splitting each line and taking what looks like the level word. Counter counts how many times each level appears, and sorted ensures a stable printed order. Converting the result to a simple dictionary keeps the output compact and easy to scan. The printed table highlights how many error, warn, and info entries you have, which helps decide whether you need urgent triage or whether the log window is mostly routine noise. Now we focus the investigation on the most recent failure because recency often matters most. This code finds the latest error by first filtering logs down to just error lines and then parsing the timestamp at the start of each line into a comparable time object. The helper called TS parses those timestamps into time values. Using max with TS as the key returns the error with the latest timestamp. That line is the most relevant for active incidents and gives you a clear place to start digging deeper. Printing that line confirms which error happened last and which subsystem is currently failing. Next, we combine severity and recency to make a short prioritized list for review. This snippet ranks problematic lines by assigning numeric severity weights and then sorting by severity and time. The dictionary sev maps error to a higher score than warn, so critical issues bubble up. A regex collects only the problem lines, ignoring routine info messages. The hits list is sorted first by severity score and then by timestamp, descending, so the latest critical events appear first. Slicing the sorted list returns the 2 most urgent entries for immediate review. Increasing the slice size surfaces more context, while shrinking it speeds human scanning but might skip useful background. Finally, we build a tiny inverted index to answer precise multi-keyword queries quickly. This code constructs a dictionary that maps each normalized token to a set of line positions where that token appears, creating an inverted index. Token sets per line drop duplicates and keep the index compact. To answer a query like error and DP, The index intersects the posting sets for the two tokens and sorts the intersection to produce a deterministic order. The matched indices are then used to pull back the original log lines. This intersection method scales to more terms and gives fast, multi-keyword filtering, narrowing your investigation to exact lines that contain all query terms. Recap: this is simple log search for triage. Use it when you need fast, explainable filtering over a log window. One caveat is it misses semantic matches that require embeddings or full language understanding. Next step: tune the severity weights and the top K slice size to match your incident priorities and reduce false positives. If practical, fast log search helps you find real issues sooner. Subscribe and watch the other incident response and information retrieval videos.